Hello everyone, I am here to present the project Deep Camera Localization. What we're trying to do in this project is we're trying to predict the robot's location based on only camera input, which is a very common problem in robotics. We're using learning method to solve the problem because first, tuning for different environment isn't necessary because the learning method only needs to train under different data sets to be able to work under different environments. The second reason is the learning method is end-to-end, which means after inference, we can directly use a result. Previous works on the problem includes MapNet and deep visual odometry, which all have their respective flaws. What we're trying to do in this project is we're trying to improve the implementation based on deep visual odometry. First, we will replace the convolution layer for a better feature extraction, and then we will add attention after image encoder for better representation of the environment. We're experimenting on KITTI dataset. We're only using the frontal camera image sequences and GPS coordinate sequences in the KITTI dataset. There are in total 11 trials. Each trial has on average 1,000 images, and the total size of the dataset exceeds 80 gigabytes. Here is the architecture of the model. So after we get the sequences of images, we're going to stack consecutive images together to get the temporal information of the translation. And then the stacked images will pass through ResNet to get the feature extraction. Afterwards, we do the attention map to get the attended context. The attended context is then inputted into a two-layer LSTM and a fully connected layer to get the actual location, rotation, and translation. So in the approach, we're using a ResNet 34 as the encoder, and for the decoder, we're using a two-layered LSTM. We eventually chose Atom for our optimizer, and the loss function is the mean square error between rotation and translation. Here is the formula. So as for the results of the model, we cannot make a comparison between our model and MapNet because MapNet uses a different dataset and uses different metrics as ours. But as we can see here, our comparison with deep visual odometry yields in general better results, both in translation error and rotation error. On the right are the results of our outputted sequences. In the comparison, we can see that compared with MapNet, our generated trajectory is smoother, which is very important in the actual localization application. And as a result, our model is not quite as accurate as the result of MapNet, and we especially suffer from loop closure, which MapNet does very well. And compared with deep visual odometry, we have generally better performance due to added attention mechanism and a better feature extraction layer. The attention mechanism is especially important because the attention mechanism can effectively filter out noises such as moving objects, running cars on the road, and pedestrians. And we have significantly better improvement in maps with less features because we are using a better feature extraction method, which works better when the feature is sparse. So as for the future works, we can first of all apply our model to different datasets, such as Oxford Robot Car, and sometimes even indoor datasets. And then we can improve the decoder structure, which the LSTM implementation right here is relatively basic. And another thing we can do is we can decrease the model size. As for now, the model size is huge and requires a lot of GPU memory to actually able to run it. And lastly, we would like to improve the overfitting by adding more regularization methods. That's all for the presentation. Thank you very much.